Welcome back to BAS 120. We're on Chapter 7. This is Part 2. We're going to walk through some more about hypothesis testing. Now remember, the whole key of hypothesis testing is to try to take our sample data, and if it falls within a region that would be reasonable to expect, then we will not reject our null hypothesis. If our sample falls into a region that's very strange, or very unlikely, or very low probability of happening, then we tend to reject our null hypothesis. So let's go through each step in a little bit of detail. So step 1 is to state the null hypothesis and the alternative hypothesis. Now we have 3 options on this. Let's say we had a test or a class, and I wanted to prove, and historically, my classes had scored an average test score of 80, and I wanted to prove that this was a very unusual class. Now notice unusual could be unusually low scoring or unusually high scoring. So I would state my null hypothesis to be the status quo, that the average test score is equal to 80, and the alternative would be it's not equal to 80. So note that if it's very, very low scores, that will have me reject the null hypothesis. Or if it's very, very high scores, it'll have me reject the null hypothesis. This is called a two-sided test, right? It means that very, very low scoring scores prove it in, and very, very high scoring scores will cause me to reject the null hypothesis. I shouldn't have said prove it in. It will reject the null hypothesis. Another scenario would be I might want to prove that I have a very low scoring class. That would be a one-sided test, the left tail I'm interested in. Or I could try to prove that I have a very high scoring class. That would be a one-sided test on the right tail. So it's important when you set up the null hypothesis to understand whether you've got a two-sided test, i.e. high or low scores will cause me to reject the null hypothesis, or if I have a one-sided test, only high scores will cause me to reject, or only low scores will cause me to reject. And the reason it's important is because the region will change. The probabilities will change slightly. So if I have a two-sided test, my rejection regions will be these shaded areas. If I have a one-sided test, this is a right tail. So in the example we just gave, this would be the high test scores. If it was the low test scores, we would just move this blue region over to the left side of the tail. And it's important to know whether you have a one-sided test or a two-sided test. All right, now step 2 is to determine the level of significance, or the alpha. How much reasonable doubt are we willing to live with? Normally it's 0.01 or 0.05. Sometimes you'll see as much doubt as 0.10. 1 minus the alpha is called the confidence coefficient or the confidence level. So 1 minus 0.01 is 0.99 or 0.95. Often you see these shown as percentages, 99% or 95% confidence level. It just determines how much reasonable doubt or how sure do you want to be. The smaller I make the alpha, the more sure I am that I don't have a type 1 error. And a type 1 error we will go through later, but a type 1 error is basically where I convict an innocent person. So step 3 is to compute the value of the test statistic. What does our data tell us? Where on this curve does our data fall? It's called a test statistic. It basically puts our data into a standardized score so we can then compare it to see what's the probability of getting that test statistic. So in this case, we did a test statistic. Sometimes it can be, depending on the distribution, it can be different things, and we'll show you that in each example. It might be a t-score if it's a t-distribution. It might be a z-score if it's a normal distribution or a proportion, but it's just based on what distribution we have. It'll give us a t-score or a z-score. They're all called test statistics, and I think of them as, what does the data tell us? What does our sample say? Now, once we know what our sample says, then the next question is step 4 is to say, well, how abnormal did we want them to be? What is our critical value? How abnormal does our sample have to be for us to reject the null hypothesis? So that's what the critical value is. So we'll show you how to go based on our alpha. We'll be able to determine what that critical value is. So in this case, the critical value is 1.86. The t is 2.60. The t is outside in this rejection region of our critical value. Therefore, we would reject the null hypothesis. Same thing over here. Our critical value of our z is 2.326. Our test statistic, or the results we got, was 5.68. It's outside. It's in the rejection region. Therefore, we would reject the null hypothesis. Step 4, you have two choices. You could do it with critical values, or you could determine what's called the p-value. So the p-value is just the probability of obtaining those test statistics or those test results equal to or more extreme than that observed from the sample data, assuming this null hypothesis is true. So for example, assuming that my coin is fair, I would calculate, and I flipped it 100 times and got 1 out of 100 heads, I would calculate the p-value would be the value of getting 1 or fewer, i.e. more extreme, heads when I flip it 100 times. Now, the lower the p-value, the more likely we are to reject the null hypothesis. Step 4, we determine the critical values and the p-values. And then step 5, we compare those to see if they're within. We compare the critical value to the test statistic. If the test statistic falls into the rejection region, we reject. If it falls into the non-rejection region, we do not reject the null hypothesis. Step 6 is just simply to interpret the results. So notice if the test statistic is in the rejection region, we reject the null hypothesis. One important thing, just like in the court of law, no, we have not proven, if we don't reject the null hypothesis, we have not proven that the null hypothesis is true. We just have proven that we cannot reject it. So for example, if we go back to our coin flipping example, if I flip the coin 100 times and I get 40 heads rather than the assumed 50 that you would get, I probably don't have enough data on that alone to get a test statistic that's going to be outside my critical value. So I probably can't reject the null hypothesis. But I haven't proven that the coin is fair. I've just proven that I don't have enough evidence to reject the assumption that the coin is fair. Just like in a court of law, I don't prove somebody's innocent. I just fail to prove that they're guilty. So, quick review on hypothesis testings. There's two approaches. And we'll show you both in all the examples. There's the critical value approach, and there's a p-value approach. The critical value is step 1. You state the null hypothesis. You decide a significance level, your alpha. You compare the value of the test statistic, your sample. Determine what your critical values are. If the test statistic falls in the rejection region, you reject the null hypothesis. And step 6, you interpret the results. The p-value approach, very similar. You state the null hypothesis. You decide your significance level. You compute the value of the test statistic. That test statistic allows you to determine the p-value, which is the probability of getting that test statistic or more extreme. And then if your p is less than or equal to your alpha, you reject your null hypothesis. In step 6, you interpret the results. So that's it for hypothesis testing. Our next video will take you through understanding the risks. Any questions? Let me know.